So this word constant, what are we referring to when something is constant? Is it really changing all the time or is it always staying the same? Always staying the same. So constant really means always the same. Let's move on to the word rate. And so let's pick apart this word rate. We've figured out rates before, right? Like miles per hour, that's a rate. So what are we doing when we find a rate, or what is a rate? Think of miles per hour, or feet per second, or gallons per mile, or miles per gallon. We're comparing. Aren't we comparing? Miles to hours, miles to gallons. So we compare with different units. We compare usually as a fraction, and they have to be different units. So let's write different units. Okay. That brings us to the word change. And not like the change we have in our pocket, but mathematical change. In math, what math operation do we usually think of when we want to figure out the change between something? Difference. So subtraction. So constant rate of change means we find the difference, we set up a rate or a ratio basically with different units, and we want to make sure that it's the same all the time. If it is, then we got a constant rate of change. We'll always have a rate of change. The thing is it constant? And we're going to check on that right now. So let's take a look at this fabric needed for costumes. Okay, so we're looking at a chart. Look at this table, and it says number of costumes. We got 2, 4, 6, 8. And then the fabric they're using in yards for the costumes. So let's just take a look at how it's changing. Let's start with the number of costumes. From this to this. That's plus 2, right? We're adding 2. Isn't it adding 2 each time? Definitely. That's pretty easy. I mean, everyone here is able to do that. How about, let's compare and see how it's changing for the amount of fabric. If we're going from 7 to 14. So we're increasing by 7. Here we are as well. And here we are. Okay. So if that's happening, looks like we have a constant rate of change. Do you see it? It's the same each and every time. We got a 2 and a 7, 2 and a 7, 2 and a 7. Now, since we do have a constant rate of change, they ask us to determine whether the relationship between the two quantities described in each of the tables is linear. Well, we got a constant rate of change, so it is linear. If so, find the constant rate of change. If not, explain your reasoning. Okay, so looks like it's linear. We can figure out the constant rate of change. Pick any pair of changes. So we've got a 2 and a 7. I'll pick this one. Okay, and Now we have to set it up as a rate. Do we want costumes per yard or yards per costume? Yards per costume. Once you look at the possible rates, it will make sense which one you want to set up. So we want fabric in yards. We're going to compare that to costumes, number of costumes. So write that down. Number of costumes. Okay? Write that down. Number of costumes. And so we want to set up a rate with that. So what was the change in the number of yards of fabric? 7, positive 7. So that's 7 yards for 2 costumes. Seven yards for 2 costumes. Let me see if I can just, that's better. 7 yards for 2 costumes. Now, what's even going to be better still is if we make a unit rate. Remember unit rates? So let's convert this into a unit rate. So a unit rate is when it's for every one of something. So here we know it's 7 yards for every 2 costumes. But let's figure this out for every 1 costume. Basically 7 divided by 2. How much is that? You have $7, you split it in half. 3.5. So 7 divided by 2 is 3.5. So it's 3.5 yards per costume, or 1 costume. Okay. So we got a unit rate. Basically now they're using about 3.5 yards per costume. So that's one answer. The other thing is this linear? Did we get a constant rate of change? Yes. So it's linear. So we can say is linear because we found a constant rate of change. So we'll just say it's linear. The fact that we were able to do all this work with it tells us it's a linear relationship. If I would go ahead and graph this, I would get a straight line. Okay? Any questions? Let's move on to number 2 then. See a couple people still looking and writing, so I'm going to give you a moment. But start looking over number 2 if you're done. We're going to basically go through the same process. Okay? You guys ready? Let's do it. So this time we're looking at distance traveled on a bike trip. So we're dividing it up into days and then the distance in miles traveled each of those days. So let's see what we have for the days. Looks like we're increasing by 1. Would you agree? Definitely going up by 1. So that's pretty easy. And so then we want to compare that to the change in the distance. From day 1 to day 2, we went up 21.8 miles. then from day 2 to 3, we could subtract, right? I'm not sure about that one. We want to do 68.8, and we'll subtract 43.6. Ooh, there I got 25.2. And then here, we're going from 68.8 to 90.6. Let's try that one. 90.6. Subtract 68.8. 21.8 again. So here's what we got. What do you think? Do we have a constant rate of change? It would have been nice if this one was 21.8. But because of this, no constant rate of change. So it's not linear. Any questions? All right. So we're going to do the same thing, but we're going to be looking at some graphs for the next two examples. You guys ready? Okay. So let's look at number 3. We're looking at a graph, and the graph says hawk diving towards prey. So you can almost picture it when you see the graph. On the y-axis, we're measuring the altitude in feet, how high up the hawk is. What are we measuring along the x-axis? Time in seconds. So after 2 seconds, 4 seconds, 6 seconds, 8 seconds, etc. So as time passes, what's happening to the height? It's lowering. So you could almost see from the picture that the hawk is going down towards its prey. Okay? So in order to figure it out for this one, because the first thing they want us to do is find the constant rate of change and interpret its meaning, well, we got to get some data like we had here. Let's make a table. And we're going to measure time and then altitude in feet. So let's start with that. We're going to look at time in seconds. We're going to compare that to feet, altitude rather, in feet. And let's get some numbers going. You always want to start at the beginning. So at the beginning, let's take a look here. At 0 seconds, what's the altitude? And when 0 seconds, it's 90. Okay, so there's our starting point. So the hawk started at 90 feet up. And then let's look at that first point, which is at 3. At 3 seconds, after 3 seconds, how high up was it? Here's 3. 60. We got another point here at 6 seconds. 30. And let's see where it ended up. Looks like if we extend this line, here at 9. At 9 seconds. Yeah. It reached its prey or a ground level, whichever one, or sea level. I go fishing up in Northern California every summer in the lakes up there, and you see some of they're water eagles. They're eagles. They're about, with their wingspan, they're about this big. They're called osprey, and to see them just swoop down when you're trying to fish, and you spent like 5-6 hours don't catch anything, they just swoop down and pick up a nice big old trout. It's just amazing and frustrating at the same time. It's just amazing to watch and frustrating that they make it look so easy. But hey, they got to eat it or else they starve. So I see the motivation. Okay, guys, let's see. We're going up by how much? On the time. Yeah, let's look at time first. 3 plus 3 plus 3. But on the altitude side, we're going down. How much are we going down by? Let's see. So let's do minus or negative 30. And 60 to 30 is another minus 30. 30 to 0, that's another one. Okay. So pick any pair. I can pick this pair right here. I'll pick this difference and this difference. Do I want to go seconds per feet or feet per second? Feet per second. So I want to do altitude over time. Let's do altitude over time. Let's set this up. Our altitude difference was negative 30 feet. Question, what does that negative tell me? Are we increasing or dropping? Yeah, we're decreasing. We're going down 30. And then it's 3 seconds. Okay. Let's change that into a unit rate. Negative 30 feet divided by 3. What's negative 30 divided by 3? Negative 10. So what does that tell us? We just found the constant rate of change. It's negative 10 feet every 1 second. What is that telling us about how this hawk is flying? It's dropping 10 feet every 1 second. You could just say every second. Wow. That's fast. All right. Now, the second part, part B, as I see some people finishing up writing that, we'll talk about that. It says, determine whether A proportional linear relationship exists between the two quantities shown in the graph. Explain your reasoning. So we want to know if there's a proportional linear relationship. Okay. And for that, the easiest way to tell is looking at the graph, guys. So I'm going to go back to the graph in a minute. Okay, you guys ready? Anyone still writing this? Okay, let's look at the graph. And what we care about to see if it's a proportional linear relationship is what happens when x is 0. When x is 0, when time is 0, what's the altitude? 90. In order for this to be a proportional linear relationship, when x is 0, y has to be 0. In other words, we want to start here at 0, 0 and go either up or down. If that's not happening, it's not a proportional linear relationship. So to tell if it's proportional linear, just look at the graph. You want to start it at the origin, right at 0, 0. Is that happening? Not a proportional linear relationship then. So the other one, this one will be, by the way, because it's starting at 0, 0. So let's go ahead and answer that. We're going to say not a proportional linear relationship. It's a linear relationship, just not proportional. And then the explanation is it starts at, let's write down the coordinates. When x was 0, y was 90. So we're going to write those down 0, 90. Not what we wanted, which was 0, 0. We wanted and expected it to start at 0, 0. And it didn't. So this one is not a proportional linear relationship. You guys ready for the last one? What are we looking at the last one? The book sales, like a bookstore, I guess. Let's take a quick look at this one. Book sales, number 4. So on the x-axis, we're measuring days. On the y-axis, we're measuring sales in dollars. Looks like thousands of dollars, by the way. So let's go ahead and put days as our first column. And we're going to put sales as our y column. And that's going to be dollars. And let's start right at the origin. So at day 0, what was our sales? 0. We'll go on to the first point, which happened at 3. At day 3, how much was our sale? $1,000. Okay. Let's move on to the next point, which is at day 6. At day 6, it was 2,000. And let's go ahead and do 9. Put a dot there. At day 9, we had sales of how much? 3,000. Not too bad. Okay, so let's see. Looks like we're going up by 3. Each time it's plus 3, which is nice and consistent. We like that. How about the sales? What's it changing by? 1,000. Each time? 1,000 each time. So we can say that we want sales per day. We want sales per day. And pick any one you want. I'll pick this one. When we went from 2,000 to 3,000 and from 6 to 9, our difference was $1,000 in 3 days. Well, that's all well and good, but let's figure out how much it was every day. If you did $1,000 per day, let's see what it was per day. So we'll do a division. 1,000. You got it? Divided by 3. Remembering, this is money. It's $333.33 per day. Okay. So we could say the constant rate of change means they sold $333.33 worth of books per day. Okay. And then determine whether a proportional linear relationship exists. Do we got it one this time? Yep. So we could say is a proportional linear relationship. Okay. Excuse, I know that P, in fact, it's bugging me too much. I'm going to just, I don't know why I wrote it so separated from the I. Starts at 0, 0. Okay. And when we go revisit direct variation next week, you're going to see why that's important. But for today, whenever you see a graph or a table, if it has 0, 0 as part of the data, it is proportional. Okay? All right, so this is going to go in your notes, everyone. I'm going to pass out glue sticks in a minute. Okay? But this will be going into your notes for this, rather than have you type in and make all these graphs by hand, which would have been a pain for all of us. We'll do it this way.